All right, here we are back with topic 10.8. We have another test to talk about in topic 10.8 called the ratio test. If I'm being honest, this one's usually my favorite test. I just find it interesting and easy to kind of spot when the ratio test should be used. So it ends up being kind of one of my go-tos as long as the series is going to play nice with what we're going to learn here with the ratio test. All right, so first things first, with the ratio test, we are going to be looking at a series. It doesn't need to be an alternating series like our last topic, so just any series is fine, but it does need to be a series that has non-zero terms. That happens to be important because we're going to do division, and so if the series has zero terms when you divide, you run the risk of dividing by zero, which we don't want to do. We have three different conclusions that can happen with the ratio test. We will know that our series converges if, when we take the limit as n approaches infinity of the absolute value of the ratio of the nth plus 1 term divided by the nth term. So that's kind of similar to what we did in topic 10.7, but we're taking the limit as n approaches infinity and we're using absolute value. Convergence will happen when that limit is less than 1. So basically, if you're thinking about what happens, that tells you that the ratio of your terms is getting smaller and smaller and smaller, which means you're adding less and less and less on to that series, helping that convergent behavior to occur. On the flip side, our series is going to diverge if that same limit of the absolute value of the same ratio is greater than 1 or infinity. Infinity is just a special case scenario where it would be greater than 1, but it does count as a conclusion that would lead us towards a divergent series. We do have a situation where the ratio test is inconclusive. That's going to happen if the limit of the absolute value of the ratio of those terms is equal to 0. That kind of means that our terms are non-increasing. So if it's not an alternating series like the one we did in 10.7, there's not a guarantee that if the terms stay the same, that will have convergent or divergent behavior. So there is an inconclusive situation with your ratio test, which is kind of a bummer. But if we can get a result less than 1 or we can get a result greater than 1, then the ratio test will give us an answer of either convergence or divergence. Okay, I mentioned that I like this test because in my mind it's easy to spot when to use it. It's really helpful if you're dealing with series that have powers of n or factorials. Because when you consider comparing the n plus 1 term to the nth term, a lot of things are going to end up canceling out when you do your multiplication by the reciprocal. So that's kind of what you're looking for. Okay, a real quick check. Our terms are supposed to be non-zero. So 2 to the n over n factorial, if we start with n equal to 1, is never going to equal 0. So we're safe there. So that means we're going to set up our ratio test with the limit as n approaches infinity of the absolute value of 2 to the n plus 1 over n plus 1 factorial. So that's my a sub n minus, not n minus, sorry, excuse me, a sub n plus 1. The n's just all get replaced with n plus 1s. And then we divide by this original because that's what the values are when n is plugged in to that a sub n formula. Now a little quick check. A lot of times your absolute values can be eliminated. All of these things are positive, so there's no need for us to keep those anymore. We don't need to change anything. We just know that everything's positive already. So I'm going to go ahead and think about this now as 2 to the n plus 1 over n plus 1 factorial times the reciprocal. So n factorial hops up to the top and 2 to the n goes to the denominator. And now you can probably start to see why this series was a good choice for the ratio test. If we think about 2 to the n plus 1 divided by 2 to the n, those have like bases. So we can subtract these powers. N plus 1 minus n is just 1. And so that means that when we simplify, hopefully I can squeeze it in here, we end up with just 2 to the first. So that's going to belong in the numerator. Kind of in a similar situation, if we think about n plus 1 factorial and n factorial, if I peel an n plus 1 off of this factorial, it would be n plus 1 times n factorial, and then those n factorials will simplify away. So we end up with just n plus 1 left in our denominator. That's a pretty easy limit to think through. As n approaches infinity, that is going to be equal to 0. And for the ratio test, we're comparing to 1. 0 is less than 1, so we can make our conclusion that the series converges by the ratio test. Okay. Moving ahead to example B, we've got another scenario that's going to be a good candidate for the ratio test. N squared is always positive, 2 to the n plus 1 is always positive, 3 to the n is always positive. We're not going to have any zero terms, so we've checked on that. If we go ahead and let's try to keep our space separate here a little bit. Think about I'm going to start up here, limit as n approaches infinity of the absolute value of the ratio. We want all of these n's to be replaced with n plus 1. So n plus 1 squared. 2 was already raised to the n plus 1, so when we plug in n plus 1 here, it becomes n plus 2 as an exponent. The bottom will become 3 to the n plus 1, and then we'll divide by the nth term, which is just n squared, 2 to the n plus 1, and 3 to the n. Okay, again, all of these things are positive, so I don't think these absolute value bars are providing much of a benefit to us. So when we go ahead and start unstacking this, we're going to have no need for those absolute value bars to continue with the process. So that numerator is going to get multiplied by the reciprocal of this denominator, 3 to the n squared times 2 to the n plus 1. And a similar thing is going to happen. We're going to have lots of things that simplify. Now be careful. N plus 1 squared and n squared are not factorials. So those don't simplify the way that a factorial does. So I'm going to leave those stacked up in our numerator and our denominator. When I look at these two terms, though, those have a like base, so I can subtract those powers. N plus 2 minus n plus 1 means I'm subtracting n and I'm subtracting 1. So that's going to leave me behind with just 2 to the first. And then a similar thing is going to happen here, except n minus n plus 1 will be n minus n minus 1. So that 3 ends up with a negative power. It's going to live in the denominator of the fraction. Okay, let's think about our limit information. We're approaching infinity, so if we were to expand this numerator out, it would be n squared plus 2n plus 2. That gets multiplied by 2. So basically, the largest power in the numerator is n squared, and it has a 2 as a coefficient, 2n squared. The denominator is 3n squared. Those degrees match, and so the ratio of the coefficients is really the same thing as the limit value. 2/3, I kind of ran out of space here, but 2/3, if we make our comparison, is less than 1. Here, let me just write this down here so that we don't have any confusion. Which means, again, we're going to end up with converging behavior. Sorry, for some reason in my notes I have written down that this is supposed to be 4/3, so I'm trying to double check my work here and see where I went wrong. I don't think I went wrong. N plus 2, n plus 1, I think it's 2/3. So the series converges, again, by the ratio test. All right, looking ahead to part C, we have something that's a little bit more interesting maybe than we had before. We actually have an n raised to the n power. I don't think we've dealt with something like that before. So sometimes with these, you can kind of think about like relative rates of growth, like factorials grow faster than polynomials do, and factorial grows faster than like n squared, for example. But n to the n power, if you imagine approaching infinity, that's a really big value raised to a really big power. So it is probably going to rival this n factorial in terms of how large it gets. So we're going to use our ratio test to help us determine whether or not this particular series is going to converge or diverge. If we're thinking about n values from 1 to infinity, that's always positive raised to a positive power, and n factorial is always positive. So I think we've met our criteria of having non-zero terms. So if we go ahead and set up our limit as n approaches infinity of the absolute value, remember we need the n plus 1 term first. So this n becomes n plus 1, and this power also becomes n plus 1. And then this factorial becomes n plus 1 factorial. That's going to be divided by the nth term, which is exactly what we're staring at. So n to the n over n factorial. And then again, I don't think those absolute values are really doing anything for us. So we're going to have the limit as n approaches infinity of n plus 1 to the n plus 1 over n plus 1 factorial times the reciprocal, so n factorial over n to the n. Okay. These factorials definitely behave the same way the factorials behaved up here. So that means we're going to be able to eliminate all of the n factorial from the top, and all that will be left behind in the bottom is n plus 1, that first term of the factorial. And then we're going to end up with something a little bit interesting here. We end up having a lot going on with this power, but a different base. So we can't subtract like we did before. We're going to separate this, I think, is the best approach. So let's separate this to be n plus 1 to the n times n plus 1 to the first. Remember, when things have like bases, we would add their powers up. So I'm kind of undoing that to show these two parts of the addition problem separately. And the reason why I'm seeing that that might be helpful is because that will then cancel out these n plus 1 terms. We still have this n to the n in the denominator. And so if we do that quick simplifying there with those n plus 1 terms now, this is a result that I'm not sure you're really going to recognize, but without going down too much of a rabbit hole, this is a particular limit that's equal to actually one of the values that we use quite frequently in mathematics, but you might not know it. The limit as n approaches infinity of n plus 1 to the n over n to the n, or you could think about that fraction all being raised to the n power, is actually equal to the number e. That's the definition for e. So it's not that I expect you to know that, but it is something that is helpful for this problem. That gives us the answer to compare to our 1 to see what's true about this series. So would this be a series that you would see on your test? Probably not, because you're not going to memorize necessarily that that's equal to e, but it is something that pops up every once in a while, and it makes it a good example for us. E is greater than 1, and when we're in a situation where the ratio test produces a result greater than 1, that means the series diverges. So we will say the series diverges by the ratio test, with a little bit of help from a definition for E that you might not be super familiar with. Okay, example D, I'm noticing we have an alternating piece here. We can use other tests on alternating series. So even though we could jump in and do an alternating series test, because we're dealing with ratio test, I'm going to check that out and see how it goes. It does say that our series needs to have non-zero terms, so it doesn't eliminate the option of having negative terms. If we think about root n divided by n plus 1, there's no chance of that equaling 0. And so what we're going to do is the same thing that we always do. We're going to set up our limit as n approaches infinity of the absolute value. This is where the absolute value is actually going to do something for us, of the nth plus 1 term. So this negative 1 will get raised to the n plus 1 instead of the n. The root will also be of n plus 1. And then this n plus 1 would really be n plus 2. That nth plus 1 term gets divided by the nth term. So that's negative 1 to the n, root n, and n plus 1, all inside our absolute values. Okay, so this time, in order to get the absolute values to go away, I'm actually going to need to eliminate, get rid of those negative 1 alternating components. All of the other parts of this are positive. And so my next step, once those absolute values are eliminated, sorry, my lights just went off. Give me a second.